Hello mathematicians, we're now going to have a look at parametric equations of curves. And as you can see by the change in colour, this is an extension 1 topic only. So I've come across very briefly this concept of a parameter before, and we've said a parameter is a single variable which controls both the x and the y values. So one variable controlling the value of the other two via a pair of parametric equations. The reason for going to a parametric approach is that often you can end up with simpler algebra than in a Cartesian approach. And a Cartesian approach is to do with the Cartesian plane, the xy plane. For a parabola, there's a standard parameterization. Now there are all sorts of parameterizations which are possible, but there's a standard one, and that is x equals 2at, y equals at squared, where a is the focal length, just as previously, t is the parameter, so as we vary t, what we end up with are the pair of x and y values. Now also, if we eliminate t from these equations, which I guess in a way we would say is the same as solving them simultaneously, what we get is the Cartesian equation, x squared equals 4. So let's have a look at what this looks like by going to GeoGebra. So here we have a single point, and that point is being calculated in accordance with the two parametric equations. And at the moment the value of the parameter is t equals negative 2.4. We're just going to make the value of t vary and look at the position of the points as we go through. So you can see that as t varies, when t equals 0 it passed through the vertex. We're going up to a high value up there of 4. Now if I make it trace those positions, hopefully, yep. So these are all the positions for different values of the parameter, and obviously what we get is the parametric equation. So continuing on from here, this is an example of how we can break up the parabola according to different values of the parameter. So for our parabola x squared equals 4y in Cartesian form, and therefore x equals 2at at squared in parametric form, we can see that when t equals 0 we're talking about the vertex, x is 0 and y is 0. When t equals 1 or minus 1, so there's symmetry as we'd expect, then the y value is the focal length. At t equals 2, the y value is 4a. So along this line here, when t equals minus 1, t equals plus 1, we've got the latus rectum. So if we make note of those things, the vertex with parameter 0, the endpoints of the latus rectum at t equals minus 1 and t equals plus 1, then what we can do is to understand the structure of the parabola a little bit better. Now there are also similar parameterizations for many other curves. One of them is the circle, and we've come across this before, although again we didn't specifically call it parameterization. So we could have two equations, x equals r cos theta, y equals r sine theta. You might remember we came across these when we spoke about the unit circle and we were dealing with trigonometry. So again, as we vary the value of theta, we're going to get different values of x and different values of y. And if we eliminate theta, and you might remember how we do this, we make use of the trig identity that sine squared theta plus cos squared theta equals 1. When we do that, then we end up with the Cartesian equation for a circle, x squared plus y squared equals r squared. So just to refresh your memory, a quick look at the parametric equation of the circle in GeoGebra. So again, here we have the point calculated according to the x value being r cos theta. So that is obviously r equals 5, so 5 cos theta. and the y value being 5 sine theta, we're going to make the angle vary from 0 to 360, and we might as well switch the trace on. I hope that's on. And away we go. So we can see that as we work out those different parametric positions, 270, back to 360, and here we go backwards, and so on. So all of the varying x and y coordinates are obtained by just varying one parameter. So let's have a look at some examples. So here in this example, we're doing a different parameterization. We have this point, C on T, and that's a parameterization for the hyperbola xy equals c squared. Now we mightn't have seen it written as c squared before. Again, that's a little bit of an introduction to extension 2, but it doesn't matter. So how do we show this point lies on the curve? The same as we always do. We put the x value in, we put the y value in, and see what we get. So we can see that that's straightforward. We substitute in our parametric equations, or our coordinates of our point in parametric form, into the Cartesian equation, and of course it does equal the right hand side. Part B, we need to complete this table and sketch the curve. Now I'll just fill these values in, so different values of t, I'll work out the values of x and y, and then we'll plot the points. So we calculate the values by substitution. Clearly I haven't tried to plot them carefully on the right hand side, but we can see that as t gets to be a bigger positive value, the x values get bigger, the y values get smaller. So that reflects this branch of our hyperbola, and likewise when t becomes negative. T equals 0 doesn't exist here because of course it's impossible, because we can't calculate a y value. Now to explain what happens as t tends to plus infinity, well, we've just been talking about that. As t tends to plus infinity, then the x values are going to head to plus infinity, but the y values are going to head towards 0. And as t tends to negative infinity, the x values will head towards negative infinity, and again the y values will tend towards 0. If we want to be technical, we can say that when we go to plus infinity, they head to the y to 0 from the positive side, and to 0 from the negative side when x goes to negative infinity. When t heads to 0 from the positive side, so that's getting closer and closer in here, then what we notice with the x value is that it goes off to plus infinity, and the x value goes towards 0, and the y value goes off to plus infinity. And as t heads towards 0 from the negative side, again the x value heads towards 0. Once again we could say 0 plus side, 0 minus side, and the y value shoots off to minus infinity. Number 9, find the Cartesian equation of this curve and describe it geometrically if r is constant and theta is a variable. So let's have a look at the Cartesian equation first of all, and then we'll go to GeoGebra to look at this particular graph. So if x is this, y is this, then if we make cos theta the subject of this first equation, then cos theta equals x minus 3 divided by r, and for sine theta over here, sine theta is going to equal y plus 2 divided by r. And then if we make use of the fact that sine squared plus cos squared equals 1, then if I square sine, I'll get y plus 2 on r squared, and if I square cos, I'll get x minus 3 all squared on r squared, and that equals 1. So therefore x minus 3 squared plus y plus 2 squared equals r squared. So I'm talking about a circle, with the center at 3, -2, and a radius of r. Now, with these equations, what happens if I keep r a constant, so I don't change the radius, but I vary theta? And what happens if I keep theta constant, so the angle constant, and vary the r? So let's take a look. So let's take a look at this. The reason I've done it on GeoGebra is because it's not a typical question, but it's an interesting one. So we're going to trace, I hope, the position given by those parametric equations in question 9 if, first of all, we vary r. So as I vary r, but theta is a value of 0, this is my parametric equation. So I'll take r back to where it was. I'll change my value of theta and again vary r. And you can see that what it looks like I'm getting drawn is just a line running out along the radius at a particular angular displacement. Now if I can clear both of those, and now I'll stop varying r and I'll just vary the value of alpha. So r is set at 8, I'll vary the value of alpha, and we can see there we get our circle. Center, as we said before, whatever it was, not at 0, 0 anyhow, and radius is set at 8. Now if I stop that one, I'll take them both back to 0, I'll reset the view, and then I'll vary both of them together. And while I'm doing that, you might make a prediction about what the curve will actually look like, if r is going to increase as the angle increases. So here we go. So were you correct? So a spiral.